Well, good evening, Caleb, Jamie. This up here. Hello. Others may come in, others may not. That's okay. This is why it's optional tonight. But I am going to go over pretty much one of each type of question. So I think it definitely will help to be here. I am recording, so I will post that if it comes through well. But I'm not going to keep you any longer. We're going to get started. So I'm going to show you an example of each type of question. It's not going to be exactly the same, but I want to give you as many hints as I can here. This is not a gotcha kind of class. We want you to learn the material and be able to repeat it on the midterm. So for section 7.1, you'll get a question similar to this. So I have two tables and I'm asked which mixture below tastes more lemony. Okay, this one's similar to the book, one of the questions in the book. So what you want to do when you get a question like that is you want to look at the units and you want to compare mixture 1 and 2. So I have tablespoons of lemon juice and cups of water for both of these. The more lemon juice I have, the more lemony flavored. The more water I have, the more watered down or less lemony. So if I look at these tables, I got a lot of different numbers. Here's the hint. You want to find a number that's on both tables. So the first one I see is for mixture 1, I have 10 tablespoons of lemon juice for 15 cups of water. Okay, so I have 10 to 15. Down here, I have 10 again, 10 tablespoons of lemon juice, but only 14 cups of water. So for the same amount of lemon juice, for mixture 2, I have less water. So mixture 2 is going to taste more lemony because it has less water for the same amount of lemon juice as mixture 1. Okay? Any questions on how that works? There's other ways, but if you notice, I didn't even turn these into ratios and fractions and reducing and all of that. I did in a way 10 to 15 compared to 10 to 14. That's all you have to do. So you're going to compare the tens. Now you could have compared something else, but you want to make sure they're in the same row as well. So 10 lemon, 10 lemon. Okay. Now, since it's just the two of you now, if you have a question, please slow me down. Otherwise, I'm going to just move on to the next one. So then 7.2 is solving proportional problems by reasoning with multiplication and division. So I'll go over an example here. So Susie mixed 3 cups of yellow paint with 2 cups of blue paint to make a green paint. How many cups of yellow paint and how many cups of blue paint will Susie need to make 15 cups of green? So the total is going to be 15, okay? So right off the bat, I'm given the total. I need to figure out yellow and blue. And it says, explain how to solve by reasoning about quantities. So in other words, again, we're not writing huge math equations and formulas, but here's where I'm going to start. Let's see, my screen shade works here. I know I have 3 cups of yellow for 2 cups of blue. So 3 cups of yellow, 2 cups of blue makes a total of 5 green. Okay, 5 cups of green. Let me do another one. Let me double it. I have 6 cups of yellow, right? You could put this in a table if you wanted to as well. But if I have 6 cups of yellow, I now have 4 cups blue, and I end up with 10 green. I need a total of 15 green. So I have to keep going until I hit 15 green. So now let me add 3 again. So now I have 9 cups yellow, 6 cups blue, which gives me 15 green. And then go back and reread the question. How many cups of yellow? 9 cups yellow. How many cups of blue? 6 cups blue. To get me 15 cups of green. Make sure you read the question because it might just ask you how much blue. Then you only need to put the blue. But this is how you would do that type of problem. Again, you could put this in a table if you wanted to, but you can also write it out like that. And make sure I don't have any other notes on there. Sorry about this smart notebook thing being on there. I thought I had a registered version, but okay. Next one, we had double number lines. I'm going to explain this one to you because I have the hindsight here of what people do wrong. So suppose you can buy a liquid soap for $2.25 for every 24 fluid ounces. So I'm making this double number line here. What did I do wrong when I made this double number line? That's kind of a vague question, but mathematically, where does it go wrong? So I went from 225, add another 225, I'm at 450. I skipped a spot, which is okay. I don't have to label every point on a number line. That's where some people thought a mistake was. I can skip. I just have to be careful because the one I skipped would be about what 675, and then I add two, not two again, and I get to the 9. So it's going right. I just kind of skipped one over here. But these numbers, if I look at the bottom, from 450 to 9, that doubles. 450 times 2 is 9. 48 times 2 is not 72. So somewhere along the line, my 225 for every 24 fell apart, and it was from going from doubling the 450, but not doubling the 48. So you can explain this various ways, as long as it's accurate. You can say, well, if I were to put one in the middle, I would see that I'd have 675, and the 72 would go there. So this is wrong. It depends on how you want to explain it, but don't just say you skip numbers because you're allowed to skip numbers. So my answer to that one would be, let me make sure I covered all my bases. The dollar amount doubled from 450 to 9, but the fluid ounces did not double from 48. It should have been 96. So I kind of goofed up on my numbering. So again, you're not required to label everything, like this space wasn't labeled. If it was, you'd want it to be 675 and 72, which means this was wrong though. Questions on that? I'm reading a double number line, finding an error. Okay, moving along. 7.4, let me go back to my notes here. 7.4 is unit rates, oops, sorry, wrong one. Proportional relationships again, so it's similar to 7.1. It's just going to have another question about 7.1 on there. So let me move on to chapter 8 already here. Be able to write a word problem involving factors and multiples. So here's an example that was from 8.1. Write a word problem such that solving the problem will require finding all the factors of 54, solve the problem. Now, in the discussion post you guys did I think it was last week. Yeah, chapter 8. It was asking you to write a problem that would require students to find all the factors of, I think it was 48. And some people wrote, find the factors of 48. Okay, that's not what we want when we say writing a word problem. So we want to write a problem that would require students to do this without actually knowing that that's what they're doing. Okay, you don't want to just state find the factors of 54. So you'll need to be able to write one. It could be about factors, could be about multiples. So an example I came up with, there are 54 members of a band. What are the ways of arranging the band members into equal rows? 9 rows of 6, 1 row of 54, just one big row, 2 of 27, right? So note that in this example, it also wanted you to solve the problem. I honestly don't remember if I put that on the midterm or not, but just make sure you know how to actually solve the problem you write. And if I was asking for multiples, okay, you would have 2, then let's say multiples of 54. You'd have 54, 108, and so on. You'd have to think, what kind of word problem could I put together that would require finding multiples? Okay. All right. Not too bad. How can you mathematically write an even number, an odd number, and is 0 even or odd? So this came right out of 8.2. How can you mathematically write an even number? In words, we said you could write 2 times n, or 2 times a variable, would give me a number that would tell me it was an even number. So in math, it's simply 2n, right? An even number would be 2 times n. You remember what we did if we took an even number and made it odd? We would either add 1 to that 2n or subtract 1 from 2n. Either way, we're going to end up with an odd number. So if 2n is an even number, adding 1 or taking away 1 makes it an odd number. And then we said 0 can be thought of as an even number since it's between -1 and +1 on a number line. Okay, so if you did alternating numbers on a number line, you get -1, 0, +1. In between has to be an even, or else you've got pandemonium. So technically, we could call it an even number. And there's another reason. You can do 0 divided by 2, right? Even numbers are divisible by 2. 0 divides by 2, you get 0, but it works. Okay, so any way you want to explain why it works, the number line is probably the most common way, but you can also say also you can divide by 2 and get 0. Okay? Divisibility rules. You want to remember your divisibility rules. So 3, number is divisible by 3 if I add up the digits, and that number is divisible by 3. Number is divisible by 4 if the last 2 digits are divisible by 4, and so on. But what we're going to do is going to ask you to come up with your own rule. You want to think about every possible combination that you can think of. So here's an example. Find a divisibility test for 20 that does not require you to do any division to actually find out. Okay, so I think you already know a number is divisible by 10 if it ends in 0, right? That makes sense. So let's use that idea. What would limit it to only 20, 40, 60, and 80? Well, I could actually call that part of my rule. So here's my rule that I came up with. Where's my answer? Okay. A number is divisible by 20 if it ends in, don't forget 0, 0. Okay. If it ends in 0, 0, 20, 40, 60, or 80. Okay. That pretty much, I mean, it's this very specific explanation because I'm listing 1, 2, 3, 4, 5 things it could end in, but that's okay. It's okay to say that. But you can also say a number is divisible by 20 if it ends in 0 and the tenths place contains an even number. Like, remember I said 0 is an even number? 0, 2, 4, 6, 8. I just thought of that. That's another way to say that 0 is an even number. So either way, this will explain if a number is divisible by 20 or not. Okay. Moving along. Halfway there, I think. So you'll want to know how to create the sieve of Aristophanes to help you find prime numbers. So maybe in this particular instance, let's say list the prime numbers from 1 to 30. You could start by drawing out 1 through 10, 11 to 20, 21 to 30. And if you remember how we did this, we crossed off 1 is neither prime nor composite, so we crossed that off. In fact, in this example, it's just blurred out. 2 is prime, but as soon as I know 2 is prime, all the multiples of 2 are composite because 2 goes into them. So this is why we're able to go ahead and cross off all the even numbers, except, sorry, I did this totally wrong and I apologize. Let me get back here. You circle the primes. Sorry about that. So when I started with 2, I should have said, okay, 2 is prime, and then I cross off all the other multiples of 2. Okay, sorry about that. And then 3 is also prime, so I multiply all the I cross out all the multiples of 3. I've already done 6, 9, already done 12, 15, already done 18, 21, already done 24, 27, already done 30. Okay, then I do 5 is prime. Cross off everything that 5 goes into. Well, I've already done most of them. I think I've got them all now. Each time I get less and less to do because I've crossed them out already. 7, I got 14, 21, 28 is gone already. 11, 22 should be gone because it's a multiple of 2. 13, 26 would be gone. Looks like I'm probably just about done. I should have the same table as I have up there. But that's how you actually do it, okay? You circle the first prime, 2, cross out all even numbers, and then continue with 3, 5, 7, 9. Okay. This one's a little tricky. And this one was in the book, so this might help you with your homework if you haven't done this one yet. So I'm going to try to explain this one verbally as best possible. Find the GCF and LCM of these very, very big numbers. Okay, it's 5 to the 15th, it's 7 to the 12th times 11. All of that's one number because it's all multiplied together. And 5 to the 21st, 7 to the 10th, 13 squared. Okay, big numbers. But guess what? It's still going to work the same as anything else. I'm writing them out to show you the rule, but once you see the rule, you'll probably be able to figure it out. But it's okay to do this too if you want. I have 5 15s here. I have 12 7s, and I have an 11. All of this is multiplied together for this number. Okay. The second number, I've got, hopefully I did this right, 21 5s, 10 7s, and 2 13s. Okay. The greatest common factor is a number that goes into both of these numbers. It's the biggest number that goes into both of those numbers. So right off the bat, this first number has an 11 in it, and the second one has 2 13s in it. But the first one doesn't have a 13, and the second one doesn't have an 11. So there's nothing in common for these two numbers with the 11s and the 13s. Okay, if that makes sense. It's kind of like a number having all these 5s and 7s in it, plus an 11. This one has all these 5s and 7s and a couple 13s. The 11 and 13 are not common to both numbers because it's only here for 11 and here for 13. So when I'm looking for the GCF, I need to actually find the numbers that don't occur in both and throw them out. And I have 15 5s in the top and 21 in the bottom. The smaller number of those are the ones that are in common. I have 15 5s up here, and I have at least 15 here. I happen to have 6 extras, but they're not common. So if I were to do this, I'd say, okay, I've got 15 here. I've already crossed off these because they're not going to be common factors. This one has an 11, this one doesn't. This one has a couple 13s, doesn't have any 13s. But here I have 15 5s, so I can circle 15 5s here. Oops, sorry about that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Did one too many. So again, what I'm doing here in the blue is I'm trying to find the GCF first. Greatest common factor, the biggest number that goes into both. These 5 don't line up with anything up here, so I can't use those. Okay. I also have 7s, but I have 12 up here, but only 10 down here. So I can have 10 here. You can also think of them pairing up with factors in the other ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These 10 pair up, but those two didn't. So here's what I have for my GCF. I have 5. The smaller number of them that I have was 15. So it's 5 to the 15th times 7. The smaller one, 10 or 12. I only have 10 in the smaller number, so I can only go with 10 for the common factor. I didn't have any 11s or 13s in common. So this is my GCF. Okay. So I factored it all out. I wrote them all out and crossed out the, paired them up by circling them, however you want to do that. But once you do that, you see the rule, I hope. 11s and 13s are not in common, so I throw those out. I have 15. I have to go with a smaller number of 5s, 5 to the 15th, and the smaller number of 7s, 7 to the 10th. And you don't have to multiply this out. Leave it like that. Okay. Now, the trickier one, just because the number gets really big, but again, we're not going to actually multiply it all out. I'm going to go ahead and erase this. Luckily, we're on video, so you can go back and boy, my computer is slow. Should have just doubled up the slide here. Note to next time, double the slide. Okay, but the lowest common multiple, that one's different. That one means what number is the smallest number that both numbers go into? So you're thinking backwards with this rule. Instead of the smallest exponent, you actually want the larger exponents. Okay? So for the GCF, I wanted the lower exponent. Wow, this is slow. For the LCM, I want the biggest exponent. So I'm going to have some 5s in it. I want the biggest one this time. I want 21. I'm going to have some 7s. I want the biggest one. I'm going to have 12. And guess what? Whatever my final number is that both of these have to be able to go into, they have to have an 11 for this number. So that's 11. I need an 11. It's also going to have 2 13s in it for the second number. So the LCM is all of this multiplied together. My biggest exponent on each term. Technically, this 11 is to the first power. So it still meets that same rule. I have to have at least the 11 and then my 13s. And you could do this by the rule again. You could count all these up and say there's 21, but I think that makes sense after seeing me do it with the GCF, I hope. Are we okay? There we go. And that just kind of sums it up here. For GCF, you use the lower exponents, and for LCM, use the highest ones. All right. This was a fun one. This was similar to number 3, I think, from this section in the homework. And I'll just show you the quick way to do this. This is numerical expressions. Be able to explain a problem similar to practice exercise number 3. So I'm going to go through this one with you real quick. 6 people in a room want to shake hands with each other. How many handshakes will there be? So person number 1 shakes hands with number 2. Then they shake hands with number 3. Then number 4. Then number 5. And number 6. So that was 1, 2, 3, 4, 5 handshakes. Now here's where it gets a little weird because it's not just 5 again. Now number 2 wants to shake everybody's hand. Well, number 2 has already shaken 1's hand. So I don't redo that. So 2 shakes hands with 3, 4, 5, and 6. So that's only 4 handshakes. And it's probably enough to already see what's going to keep happening, but I'll do one more. So now number 3 is already shaken hands with 1 and 2. So 1, 2, 3 handshakes for person number 3. So 4 is only going to have to shake 5 and 6's hands. And 5 is only going to have to shake 6's hand. So it actually decreases 1 each time. And if I want to know the total, how many handshakes will there be, that implies addition. I just add those up. 9, 10, 11, 12, 13, 14, 15 handshakes. Now, the book also gives a formula that it's 6 times 5 divided by 2. Since there were 6 people, we do 6 times 6 minus 1, which is 5. And then we divide that by 2. So you could do this either way. I kind of like the visual to show you, but it is a formula and it's given in the book as n times n minus 1 all over 2. So 6 times 5 divided by 2. All right. This one's not too bad. When I first read it, I thought it looked really complicated, but it's much simpler than they're making it. This is 9-2, which is expressions with variables. Young has lollipops to distribute among goodie bags. When Young tries to put L lollipops in each of 6 bags, she's 1 short. Write an expression for the total number of lollipops in terms of L, and then briefly explain. Please be careful when you see the word explain that you actually do put this in some kind of words too. Don't just write the expression. So if I have 6 bags with L lollipops, that's 6L lollipops, but I'm 1 short. So I subtract 1. So that's all I do. 6L minus 1. Okay, because I have 6 bags with L number of lollipops in it, and then I take away 1. Now, you could also write it as 5 complete bags plus L minus 1. This is probably the most logical, 6L minus 1. Okie dokie. I do like that though, because it's showing you that you have 5 full bags and you're missing 1 out of the other one. But either way, they work out the same. Okay. I wanted to do one more of this type of problem that we did in the class meeting. This is reasoning about equations, reasoning about relationships here. So I have this scale. We always like to equate equations to scales. I have 238 over here, over here on the left. And I also have 149 on the left. And it weighs the same as X plus some 241 items. Okay. First thing I want to do is I want to look at 2 of the numbers that are very similar, or very close. 238 and 241 are very close together. Okay, so I'm kind of putting those together. And I'm saying on the right-hand side, 241 plus something else balances out 238 plus 149. So I'm looking at the relationship to each other. 241 is 3 more than 238. So I need to put 3 less than this other number on the other side to balance it out. I need to put 146 over here in for X. Let me put that actually right on the X. So that's how we're reasoning this out. 238 are close together. 244 is 3 more on the right than the 238 on the left. So to balance it, I need the 149 to take away 3 to balance it on the left. Again, we don't want you to just add this up and subtract 241 and get the answer. We want you to kind of write this out in words the way I said it, or in your own words, but of the same meaning. Okay. All right. This one, now this one originally wanted, I believe, strip diagrams made and so forth, and we changed it to just solve it algebraically because it's hard to draw all this stuff out on a test paper. So be able to solve words with algebra. So here's an example. A candy bowl contains 723 candies. Some are red, the rest are green. There were twice as many green candies as red candies. How many red candies are in the candy bowl? So you've got a bunch of information here. You know the total. You know that you have 2 colors, red and green. You know that you have twice as many greens as red. And the bottom line is they're not asking how many greens and reds, they're just asking how many reds. So make sure you, again, read the question and see what they're asking for. How many reds are there? So here's how I would start. You always want to start by creating a variable to represent something. So I said, let's let n be the number of red candies. You could say R for red, X if you want to use X, doesn't matter. We use n for number a lot. So there are twice as many green candies as red candies. So if red is n, green must be twice as many, so 2n. Okay, that's why I started with red. Now you could have said let n equal green, the number of green, but then red would have to be a half n, which, you know, just to avoid fractions, we probably don't want to do that, but you could, okay? However you want to do that, it's fine as long as you stay consistent. So 2n is the number of green candies. What else do we know? We know the total is 723. So I know that if I add the reds and greens together, 2n plus n, or 2n plus 1n, I get 723. So 2n and 1n are 3n. That gives me 3n equals 723. Divide by 3, and I get 241. Now, n, don't forget, n equals the number of red, and we asked how many red, so that's the answer, right? 241. If they said how many green, this isn't your answer. This is just n. Number of green is 2n, and you would have to, multiply by 2. Okay? Very important to reread the actual question and see what they're looking for. All right. One more. Thanks for hanging in there with me. This one is the patterns. And in the past, this one was really tricky for people. That's why I wanted to do one more exact example of what I'm looking for. So, oops. When you're given a pattern like this, you want to look to see how many images are in the pattern before it repeats. And you can number it if you want to, but I can see I start here. That's my first one. Then I go to a square, so I have an arrow, a square, and a triangle. And then it looks like it starts to repeat already. And so on. Might as well finish this up real quick here, just to be picky. So 3 is the size of my repeating pattern, which is why the triangle is a multiple of 3, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. If I count all the way to 2,459, alternating between the arrow and the square and the triangle, I want to know where I end up. What shape do I have at 2,459? That number is too big to fit on my smartboard. Okay. What shape would be above that? Well, we don't want to actually do that. That's way too much work. Come on, calculator. So here's the steps. Take my number, 2459, and divide this into groups of 3. I have 819 times that I go through this cycle, plus some parts, right? Well, let's look at what 819 is times 3. 819 times 3. That gets me to 2457. So after going through this many times, I get 2,457 as a triangle at the end of a pattern, okay? So then 2458 starts back at the 1, and 2459 would then be under the square. So let me do it that way just because the numbers are big. So my answer is that it would be on the square, because then the next number is another multiple of 3, which puts me on the triangle, 2460. All right. Now, I know I didn't type up the steps, but I'll say them again real quick. You look for your repeating pattern. You identify how many images are in that pattern. You take your big number that they're giving you and you divide it by that number and throw off the decimal. Multiply your number 3 again by that number you got in your calculator without the decimal, and then add until you get to the end. Continue creating these patterns until you get to the number you're looking. All right. That completes, I think, everything that I had. I have it on another screen, so let me just double check if I did everything I want to do. Okay, that's it. So do you two have any questions? Thank you, Kate.
The only question I had was on the divisibility rules. Are we going to be asked about the ones that were in the video that we had to watch, or just the ones that were covered in the book? Or are we just gonna be asked to make our own?
You're going to be asked to make your own. So you should know them because they may be part of, you may use it to help you create another rule. But you are going to be asked to create one.
All right, thank you.
Okay, thank you. Have a good night.